All right, here we go. I'm going to introduce the moderator for the first this technical paper session, Mr. Jeffrey Bowles. So here you go. Take it away, sir.
Thank you very much. Good afternoon, everyone. Or I guess it's still morning, so good morning. Thanks for taking some time out to come and sit through the technical presentation today. Again, my name is Jeff Bowles. I'm a naval architect with the DLBA division of Gibbs & Cox. So the panel that we're going to have now, or the discussion session we're going to have is a unique group of papers. We've got some mechanical piping type stuff. We've got some launch and recovery stuff, as well as some model testing focusing on seakeeping with a hull form that we all know and love from the last year's MACC, or the most recent one, the General Prismatic Planing Hull. So up first today we have Jesus Herrera, who comes to us from Viega ProPress. He's their Marine Program Manager. He's been working in the shipbuilding industry for 10 years, but has 25 years of engineering experience in the mechanical engineering field. He graduated from the University of Dayton in 1993 and spent 20 years at Electromech Corp. And then had a couple of brief stints, one at Austell and then one at Ingalls Shipbuilding prior to moving on to Viega ProPress. So the interesting thing that I learned about Jesus in speaking with him is that he lives on a classic sailboat. He's got a 54-foot long 1976 Sparksman and Stevens design, and he travels up and down the East Coast in the Bahamas wherever the winds take him. So we're glad that he ended up here with us today in order to share a little bit about what he does. So with that, I'll turn it over to Jesus. Good luck.
Good morning. Okay, yeah, that sounds okay. So today we're going to talk about selecting mechanically attached fittings, press type. Traditional piping systems are defined in several standards. ASTM F1155 is probably the most basic one of those standards. It defines that piping systems must comply with ANSI, Coast Guard regulations, and ABS rules. Some of those examples are, flange connections, socket weld joints, flared, brace type joints. Some of these obviously have heat components to them to achieve them. And then you have threaded piping and flexible couplings. ASTM F1155 does not contemplate mechanically attached fittings. Not all of them anyways. But the scope does describe what the minimum acceptable requirements are. The document doesn't intend to select materials, does not limit the selection of materials strictly to those that are on the standard. It says that you can also include other materials that are superior or acceptable to the regulatory bodies. And it gives you a list of things that you have to meet in order to prove what those requirements are. So ANSI B31, so you have 46 CFR 56, and any Coast Guard letter will give you that. And then you have your ABS rules. And I'm showing you an example of the fittings that we produce that have all those qualifications. And on our approvals, we've included the ANSI references and the CFR reference as well. So there's also mechanically attached fittings that are included in ABS or any other class society. Those are governed by IAC's unified rules. This is a much more expansive selection of mechanical joints. And it's not perfect, but that's what we have. And you can see press fittings in there as part of it. And then finally, we get to the supreme law of the water, right? Not the land, but definitely the sea. And that's NAVSEA with MIL Standard 777. This applies to surface combatants, but also the Coast Guard. In 2018, they went through an exercise to see how they could introduce press connect fittings into the technologies that are allowed on board. And instead of changing ASTM F1387, which is the governing document, they decided to add a standard, ASTM F3226. And that standard then is what governs Press Connect. Now, even though this was the first introduction, it only included 2 systems. And that's a win. It's recognizing that press has a place on board ships of this caliber, but it wasn't great. So we undertook a project with NSRP. We joined forces with MACC, Bath Iron Works, Ingalls Shipbuilding to test fittings to ASTM F1387. 1387, if you look at the 6 different fittings that are defined in there, does not include press, like I mentioned before. That's included in 3226. But because it's considered a superior standard, the qualifications are equivalent to butt welding, we wanted to show that there are fittings out there that, even though they're called press, they do significantly perform better than just at 3226. The conclusion was that there's now Viga Mega Press Cooney and Viga Pro Press in copper that are NAVSEA approved. The NAVSEA approval letter, which you can see there, has several important aspects to it. The highlights are it's 1/2 inch through 2 inch. It classifies the systems as 250 PSI. 3226 is the basis of the approval, but then the extended qualifications such as shock, vibration, and pull-out want us 17 additional systems to be used on board. Of those, you can see chilled water, potable water, electronic freshwater cooling, diesel engine freshwater cooling, and others. You know, they are significant systems on board that are considered essential. The current configuration is limited to couplings because there's an additional paperwork exercise that has to be done, shock extensions, to get additional shapes to be approved. The additional shapes were recommended as part of the NSRP project, and they include elbows, 45s, adapters, flanges, tees, reducers, etc. And that process has been undertaken by Gibson Cox as part of the FFG 62 program from Fincantieri to get that done. That should be done in the next couple of months. At Viga, we believe that you should have a choice in what tools you use. So we have a variety of tools that you can use to match the arsenal of tools you have on your ship or on your shipyard. We have our own personal tool that is hydraulic. It's spark free, so it's good to do presses even when there's fluid coming out, partially flooded compartments, fuel, etc. Then, you know, there's the Rigid and Milwaukee and Hilti, and there's more that have the tools to match. Finally, for the NAVSEA approval, there's a special set of jaws and rings that you'll need to do those. These rings have greater tolerance to match the requirements of the presses and the performance characteristics. The features and benefits that mechanically attached fittings provide and our system provides, it's inherent fire risk mitigation. There's no hot work. It's cold press technology. The last 3 years, there were 600 plus ship fires documented during construction, during operation, and on average, every 7 years, the U.S. Navy loses a ship to fire. The most recent example, the Bonnie Richard, you know, $3.2 billion repair, and the ship ended up being decommissioned because it was too expensive to repair. You can expect upwards of 70% of labor savings just from pressing instead of bracing. And there's additional cost reductions that have to do with no firewatch, no gas freeing, no chemist. You minimize rework because the first time quality is integral to all of our products. NASCO has done studies that show that our fittings have contributed to a significant return on investment, exceeding 100%. So yes, they do have a 70% labor reduction, but when you consider the other aspects as testing, they don't have to clean the system. They can pass hydro the first time around. They don't have to go back and repair 3 or 20% of their braces. It ended up making them a whole lot more money that way as well. And that's why the return on investment exceeds the actual value of the product. The system is perfect for dry fitting, but you can even use it when there's fluid coming out. It's consistent, wet or dry. It incorporates Smart Connect technology, so an unpressed connection will fail hydro at 5 psi. There's a visible cue of water in this case that'll show you when there's a connection that wasn't pressed, and you don't have to stop your hydro. You can go ahead and press it while it's in service, while it's under pressure. So long as the insertion is in there, you can go ahead and keep on moving. So you wouldn't have to cancel a test just because of that. We also got a ProPress NAPC approval. Now, this one was even a surprise for us because all we did for ProPress was an exploratory shock test. We took a 1/2-inch fitting, put it on the shock test machine, and shocked it. And the tech warrant holder was so impressed with the system that he gave us a letter. Now, it's only 1/2-inch couplings, but the intent of the tech warrant holder is to get interest in the product from other areas of the Navy so that we can continue to extend the testing that's necessary to extend the range and applications. These products that you're seeing today are currently in use in other areas that are not the Navy. They're in Coast Guard MSC ships and commercial vessels. On a much more expanded range of materials. We offer steel, stainless steel, copper, and copper nickel systems. What are the next steps to increase acceptance, etc.? So for MegaPress CUNY, we're finishing the shock extension paperwork. As I mentioned before, that's being done by Gibson Cox for the frigates. ProPress, we need, again, additional testing to increase the range. We offer these systems up to 4 inches, and so that's crucial to get it wide acceptance and wide use. Our initial conversations with the tech warrant holder indicate that they are very interested in extending the size and extending the parts that are used, so the different shapes, and so we're moving forward. And we've done internal shock testing for the 2.5, 3, and 4 inches, and we know we can pass, so it fares very positive for us in that sense. For those of you that will download the presentation at some other time, there's some videos that I incorporated into it so that you can see the benefits of it and the different features of the product. Are there any questions? So if there are no questions, I thank you for your time. Have a good day.
you're ready, right? Okay, folks, thanks very much to Jesus for an interesting presentation. I've been familiar with Viego ProPress products for years, but I didn't recognize they had the return on investment that he's claiming there. That's pretty impressive. Moving on to the next topic, which is completely different, has to do with sea keeping in waves of a high-speed planing craft. And our presenter today is going to be Peter Bandick. He was an undergrad at Michigan as a naval architect, and then he got his PhD from Michigan as well in 2009. Focused on nonlinear ship motions in seakeeping, which was the subject of his dissertation, and has been the focus of the majority of his career. He's currently at Marin USA in the East office, the East Coast office. The Marin has a office in Houston as well in the United States, but Peter is kind of the head honcho at the East Coast office and collaborates with both the Houston office and those in the Netherlands as well. The fun fact about Peter is that he has taken up sleeping as his hobby recently after welcoming a pair of twins into his life about a year ago. So he and his wife like to catch as much shut-eye as they can. So with that, I'll hand it over to Peter. Thanks.
Thank you, Jeff, for the nice introduction. So as Jeff said, my name is Peter Bandick, and I'm going to talk to you about fast boat simulation. And you might ask, do you mean fast boats or fast simulation? And the answer is both, and we'll talk about that. By the way, the scope of the paper changed a little bit. It was originally on the GPPH, but this is maybe a bit more instructive for you guys, for the audience here. A lot of this work was done by my co-authors, Pepijn de Jong and Matteo Banci, who are in the Netherlands headquarters, and so if you have detailed questions, I may have to refer to them, but I'll try to cover as much as I can. So, what are we interested in here? What we are talking about is the behavior of small, fast vessels in a seaway, and what we want to do is see if we can identify operational limits. And there are several ways you could do this. Marin is pretty well known for the model testing facilities, so of course we have that capability. We also have full-scale trials instrumentation teams. We can do that as well. And in the past, say, decade or so, we've been doing a lot more effort into numerical simulation, code development, things like this, and in actually trying to tie all of these fields together. So we can use any of those approaches to determine operational limits, and there are also some other use cases that I'll mention, and that is in respect to training and simulators, and also onboard decision support. So when we talk about small, fast boats operating in waves, what are we most worried about? Well, the most common thing you encounter are impacts or slamming, and that results in high pressure in the bow, large vertical accelerations. These can lead to discomfort, structural damage, personnel injury, something we want to avoid, or at least have a way to assess the performance of the ship or the boat. You also have issues like bow diving and broaching. These can include surf riding effects. For broaching, for example, you're actually riding the crest of a wave and you have no control authority or very reduced control authority over your rudders, and as much steering as you might want to put in, you don't go where you want to, and that can lead to dynamic loss of stability, including things like capsize. Another impact that happens on smaller boats is swamping. This can happen in quartering conditions. You get waves that'll break typically over the side, and if your water ingress exceeds your egress, then you have a problem. You've taken on too much water, and that can lead to some very bad things, loss of stability, even up to capsize. So, how we will look at investigating these operational limits. As I mentioned, we can do model tests. They can be difficult and they can be expensive from the point of view of a complete operational envelope evaluation. You talk about your different design condition and all of your other loading conditions and a number of sea states for a number of speeds, for a number of headings. it's quite a lot. It's quite a lot of testing to do. Trials are great. You reduce a lot of the uncertainty about scale effects and approximations that you make with other methods. But then you're sort of limited into what environment you operate in. Sometimes you don't really know what that is. You have wave buoys or some kind of other devices, but it's hard to actually control the environment you're operating in. And you can typically miss extreme values. For example, you wouldn't want to subject a crew during trials of very high impacts if you can avoid it. So that's something better left for model tests or even simulation. Simulations are great, but they need to be validated, and that's really where we're focusing on. Not just having a simulation tool, but having one that reflects reality that's based on experience from model tests or trials. And one note here, a lot of times investigations follow operational incidents. You don't know you have a problem until you've had it, and what we're trying to do is be a little proactive there and show up some warning signs before we get there. So this is a little 2 videos from model testing. I'll show on the left side you have the Dutch Navy's Frisk, which is I think a 11 or 12 meter rib, and Coast Guard long range interceptor. If we could queue up those videos separately. So this is a bow quartering case. You see it's pretty severe. You have a lot of impacts and slamming as the boat comes out of a crest, and then but overall it's not terrible. The LRI tests are a bit more extreme. If we could cue those up. These are pure head sea cases. There's not a lot of rolling, but you can see the boat is it's nearly jumping out of the wave crests here. So next slide here. So that's model testing. I'll talk more about that in a little bit. The next idea for full-scale trials, we've done something similar. We have a performance at sea group that can instrument, for example, this Frisk rib with a data acquisition system. It's basically you can imagine it's a larger scale version of what we would use in our basin. And then you want to measure the environment you're in, and that's using the onboard instrumentation or local wave buoys. Again, it's sort of difficult to know exactly what you're operating in and exactly where you were, but you have a lot of data that maybe you could correlate on a statistical basis. This is an example of the sort of instrumentation, video recordings, and speed and motion channels, and there's actually long video, but I didn't include it here. It's in the presentation. Okay, so comparing model tests and trials, what can we say? Well, model tests actually replicate what we see in the full-scale measurements quite well. There are some notable differences. On one hand, in the basin, when you have a model that's this small, it's completely self-propelled. Everything is on board. There's an autopilot. There's nobody steering. And in the full-scale trials, of course, you have a pilot, and their behavior is going to be different, right? If you tell him to do something, him or her to do something that may not exactly reflect what you see in the basin. The other issue, as I mentioned, is it's hard to know exactly what environment you're operating in, but we can do some correlation from statistics. Full-scale data is great, again, but it's hard. It's hard to know exactly where your limit is for your extreme events, because you don't necessarily want to or can be there, depending on what the sea states are like when you're conducting trials. So, on to simulation methods. That's where we're sort of heading. more recently, and there are a lot of joint industry projects that have led some of these developments, and some other projects like the FSSS is a fast small ship simulator. I'll talk about that a little bit more. When we develop our simulation methods, we sort of come at it from two approaches. One is a simplified 2D methods, or these what are so-called strip methods, where instead of solving the full hydrodynamic seakeeping problem for the entire boat, you break the problem up into sections. And in this case, we use a generalized form of the von Karman impact method to solve for and couple it to the 6 degree of freedom motions of the boat operating in a wave field. And there are a lot of approximations that go with it, but the upside of this is that it can be very nonlinear for impact type problems, and it's very fast. So you can use it for real-time applications. What's missing here is you do miss some of the three-dimensional effects and wave damping. So for example, you couldn't use this method to predict wave resistance of a boat. Higher fidelity methods, we have some 3D panel codes. One that we particularly use for high-speed applications is called PanShip. It can be nonlinear. It has a lot of tweaks and dials and things like this to control exactly what level of fidelity you'd like to get. But the best answer you can ask PanShip to give you takes an incredibly long time to get, even on a high-end sort of workstation. But sometimes it matters to get the answer as accurately as you can, and so we use that tool quite a bit, and we use sort of different variations of these methods depending on the problem that we're trying to solve. PanShip, there's a nonlinear version. I'll say semi-nonlinear to be more technically correct. But it's been extensively validated. There are a lot of publications on it, both for fast displacement ships, high-speed planing craft, specialized vessels like multi-hulls, foil-assisted boats, and things like that. PanShip nonlinear is the one we're more interested in for this problem, particularly because it can handle the impact problem that we're interested in. On the right-hand side, you see from a previously published presentation, I think on the Frisk, a comparison of the pitch time trace and the vertical acceleration time trace comparison between model tests and the nonlinear version of PanShip for, I think, a regular wave condition. This is just an example. If you're interested, there are plenty of publications and other work done like this. For the generalized Karman impact method, this is a more recent development. This model is developed under Marin's extensible modeling framework. So think of this as a generalized software development framework with specific applications for maritime. So a lot of our simulators are built on this framework, and you can plug in your own modules. And so we have a Karman model there. And it can tie in to do a whole ship simulation in wind and waves. You can put on whatever kind of propulsion system, autopilots you want. This is a sample comparison of what you'd get for a typical validation. On the from top to bottom, you have the heave, pitch, vertical acceleration, and speed for the Frisk model at 20 knots in a 4.5 second regular wave with a wave height of 2.5 meters. Left side shows the experiment, right-hand side shows the simulation results. What's interesting to note here is that the model tests are done with a fixed RPM based on calm water resistance data. So you see quite a lot of speed loss in the lower left figure. You see that actually the speed varies between 10 and 15, even though you dialed in an RPM that in calm water gets you to 20 knots. On the right-hand side, you'll see that the orange line is set up in the exact same manner as the simulation, meaning that the RPM is fixed, but there's an incredible mismatch in the speed in the lower right figure. The speed is much higher, which means that the added resistance and due to the wave impacts and other things are not properly accounted for by the model, but we know that that's not what we're worried about. We're worried more about the impact problem. So the way to get around this is to actually apply a speed controller so that your simulation matches your model test. And this is important because then you match the encounter frequency of the boat encountering the waves. Of course, it's a different scheme, but this gets you much better comparison with predicting the loads and the accelerations. So as you can see, the blue lines there with the speed controller match the model tests quite well. And then if you take those peaks from those peak or mean values from those previous time traces, run them for a bunch of conditions, speeds, periods, wave heights, you can collect some results like this. This is a sample of what we would do for a validation. You can see on the left side there are figures for 20 knots, on the right for 30 knots. The black markers are experiments, orange markers are with a fixed RPM, in the sense, again, the orange and the black line are set up the same way, where they're using the same RPM, but in fact, this blue line with the surge autopilot is a preferred approach. And now that's evident on the left-hand side that you get a much better value, much better agreement in the mean speed, and it doesn't make much of a difference in the heave and pitch extreme values, but it's clearly notable in the vertical accelerations. It's also worthwhile to point out that at higher speeds, the speed loss doesn't seem to matter much between the speed controller and the fixed RPM, because you're relatively in the right. They agree pretty well as it stands. So this impact model that I just showed it's interesting. It has its limitations, but it has some application for large vertical accelerations, impact type problems, and that's an option that we can use for operational limits, as well as the panship code that I discussed. But we have some other applications. For example, real-time fast boat simulation and decision support on board, and both of those applications do require significantly faster than real-time prediction. You're not going to bring a supercomputer on your rib to do your prediction, right? You're going to need something that runs on a laptop or something that can be put on board with relative ease. So this is a bit of I wasn't sure whether to include this table, but I'll walk you through the sort of logic and what you're sacrificing and what you're getting as you progress from the highest fidelity to what would seem a lower fidelity approach, but actually checks the boxes that you're interested in. So going from top to bottom, you have this nonlinear version of a code, and that's about 1/1000th real time, meaning that if you want 1 second of simulation, you have to wait for 1,000 seconds for that to happen. And these performance numbers are based on a typical laptop or desktop. If you put it on a higher end machine, maybe you could get a factor of 5 or 10, but this is just for as a reference. There is another, for this application for high speed boats, there is an approximation where you can remove the radiated wave effect and get pretty close agreement, and then you're a lot closer. You're about 1/100th, and if you go further, you can go to the linear version of panship, all the way down to what's called panship IRF. That stands for impulse response functions. That gets pretty fast. That's where you've solved the problem once. You've taken all of your pressure distributions, generalized them for use in the time domain into what are called impulse response functions, and then you can use them in a simulation. What you've lost then is you don't have a pressure distribution anymore. You can, because you've linearized the problem, it's hard to change speed dramatically, and everything is linearized. If we go to the XMF Karman model, you'll realize that we're still making a big approximation on the radiation problem, but we've solved the speed variations and impact, and actually the performance is substantially better. It's about 100 times faster than real time. So how do we use this approach in our fast boat simulator. Well, I gave you an example of the validation that we typically do. So we'll develop a code with a specific use case, like impacts of planing boats in waves, and we'll have model test data to validate it. We also take into consideration the full-scale data or operator feedback, and we use those two pieces to build our simulators. For example, this fast small ship simulator. It's on it's mounted on a structure with 2 seats. In this illustration, it's shown with screens surrounding you. I think the most recent version is actually a projection, and the whole platform moves as it's being operated. This is used for human factor training, and it allows you to do things in a safer environment. So if you're predicting loads of 5 Gs, you don't necessarily, well, you're mechanically limited, I think, to maybe a little bit lower than that, but you can dial it down so that someone who's doing training won't hurt themselves too much on this simulator before they go out on the boat. And it also helps you increase your availability of your actual assets. And we can also use it for design exploration. For example, you can dial in a model, have somebody drive it, see how it feels, so the other application is decision support for high-speed craft. So this has been presented a bit here, actually, I think yesterday. And you have 2 obvious issues. One is immediate injury due to large impacts, and the other is a gradual buildup of injury over time. I think there was a presentation yesterday that talked about that a little bit. And the latter one is a bit complex. It involves a lot of science from fields beyond the maritime industry, and I think we can leverage those. But the immediate impacts, that one we are getting a better handle on. It still has a challenge because you essentially have to do a lot of things all at once in better than real time. You have to measure the wave field. You have to have a model that predicts what the waves will be doing in the near term, and you have to have a way to simulate what the boat will do in response, and you have to way to turn that into some kind of a guidance or recommendation for the operator to do something else if that's an option. So any of those pieces alone are challenging. Putting them all together in a box that you can install is really complicated, but that's where we see an application in the future. And so the simulation model that I mentioned can solve one piece of that puzzle. For long-term exposure, as I mentioned, this is something that we're investigating with some other partners. And well, first conclusions are that actually long-term injury does occur on a regular basis, even when experienced drivers are at the helm. And so we may need to update procedures or have some other guidance. It would be nice to essentially say, give some feedback about this may not seem like a serious impact, but long term this could be a problem, and you may want to change the way the boat is being operated. So to summarize, we went over the small, fast boats operating in a seaway. Talked briefly about model tests and full-scale trials. Sort of leading us down the path towards simulation has a lot of value here. The direct use case is operational limit evaluation because it's quite effective at doing that, and then the other use cases are these simulators and decision support systems. Thank you.
Peter, thanks for that great presentation. Questions for you, or perhaps hopefully you can answer them. The software that you're using for the impact strip theory solution, how does that compare to PowerC, which was developed here in the United States years ago? We use that in our office. We've got a seat for it, which is a very similar type program, and it's based only off the keel and the chine. And so we've used that with some limited success in the past. So I didn't know if you were familiar with it and how that compared to the the simplified software that you were using? That was my first question. And the second question is, when you get into the numerical simulations and you had that scale of pan chip down to the von Karpman, where in that do you find is the minimum level of acceptability in order to get good correlation long term with the model test and the full scale testing? Thanks.
Right. Thank you, Jeff, for those questions. So the first one, the old the original paper from von Karman and Wagner, they were impact methods that included eventually something with a spray route, but there was never anything about wave propagation. And we still follow that approach, but instead of being in calm water and a flat sections coming in vertically, we allow for vertical velocity, rotation, and we take into account the incident wave fitting up to that section. So it's a bit generalized in the sense that it's the same fundamental theory, except it's generalized to do at least the 3 degrees of freedom that you have in the 2D plane. And it's also generalized to take into account the incident wave and how it conforms to the section. But other than that, I don't know that there would be much difference. And as far as your second question, yeah, it's the usual. It depends. If you're telling me that your boat is primarily doing high-speed operations and you're really interested in pressure distributions or structural loading, then I'd say that pan-ship nonlinear with that high-speed approximation is a good choice. If you're transitioning or you're a displacement hull, let's say if you're a displacement hull operating in small to moderate seas, I would use the linearized version. And we've done cases before where you use the linear version up to a certain threshold limit, and then you check the nonlinear to make sure that things are in relatively good agreement. And then the Karman model is really for planing hulls in waves, right? The moment you reduce the speed, it's not very good. The moment you have any sort of you have to know where the limits of the method are. Thank you.
Okay, everybody, we're going into the third presentation for this seminar. So thanks for staying put and giving some attention to our authors. So our third speaker today is Amitai Peleg. He is the CEO of SealRTech, is the way I like to try to pronounce it. They develop autonomous launch and recovery systems for manned and unmanned vessels for Navy, military, and research type service. Amitai served in the Israeli Navy, Special Forces Operations Command with a commanding officer on interceptor type craft. He has over 4,000 operating hours on surface vehicles, including numerous launch and recovery operations. By schooling, he's a mechanical and marine engineer, and he's designed and built unmanned surface vehicles for the defense industry over the last 5 years with a couple of different companies, where he's really started to focus on launch and recovery systems. So with that, I'll go ahead and bring up Amitai. Thanks.
Hi everyone, glad to be here. As Jeff said, I used to serve for the Israeli Navy Special Forces, operating small boats, doing a lot of launch and recoveries. And in the years to follow, I was involved in designing, building, and testing unmanned surface vehicles. So we're going to make a short introduction. We'll talk about the need of autonomous launch and recoveries, the challenge, because it is a great challenge, and a little bit about setting market requirements and how exactly does SealRTech fulfill this set of requirements. So the images you see on the screen, I was operating boats like the one on the top. I believe one of the companies here sells these boats. We did a lot of launch and recoveries in harsh sea conditions at night. Had my share of accidents doing launch and recoveries, of course. And then in the following years, I've been designing USVs for Rafael and Elbit systems, which brought me to understand that someday someone will have to solve this issue of launch and recovery for unmanned boats, because you cannot use unmanned boats without launch and recovery system. This is a short teaser video which will go into a little bit more depth soon. So what is the need? I mean, I think everyone in this room understands that in the future we're going to use a lot of unmanned surface vehicles. And right now it seems a little bit hard. For me as a boat operator, as an ex-Navy SEAL, I used to think that there are things that only tough men can do at sea, but you know what? It's not true. The first thing I learned on the Rafael project for the USV, they installed an automatic pilot on a jet boat, and I told them, guys, it's not going to work. You have to be so experienced driving a jet boat because it skids and you need to learn how to drive it straight. No chance. But they connected an automatic pilot on a jet boat, and it was driving as straight as it can be, much better than any operator I've ever seen. And that kind of changed my perspective about it. Now, for the USV boats to be fully adopted by navies and coast guards, you have to finish this problem of launch and recovery, okay? And that's an actual missing link in this entire industry. And if we're talking about the manned market, so obviously us, the operators, the decision makers, the people who handle the lines, we make the mistakes that limit the operational capability, the sea state that we can work in, and we are causing most of the accidents. So if I'll have to divide the challenge into 3 sectors, one would be the operational one. I guess you guys have seen these videos before. Side recoveries on the top. In this case, my estimation is that this accident that you're going to see is the responsibility of the driver, who pushed a little bit too far forward and lost tension on the painter line, but also for the crane operator, which started pulling a little bit too soon when the boat was sideways. All decision-making made by men caused to a very, very dramatic accident. If we're talking about stern ramp, I've tried this myself. You have to be a very, very brave boat operator to ram up a stern ramp in high speed, and it's also very dangerous, okay? So what we say is, let's try to get the men out of the loop of the decision making and action taking and try to automate it. If we're talking about USVs, I don't know how many of you guys operated a USV before, but as for today, the last bit of a USV approaching a pier or approaching a ship in most companies is done by remote control, okay? For that part, driving a USV is actually harder than being on the boat, because you have your narrow vision of the camera, you're not feeling the waves, so it makes it harder. In the, I guess, near future, when the unmanned surface vehicles will be talking to the launch and recovery systems, that will be fully automated, and that will actually work better. And if we're talking about the engineering challenge for the engineers here, we have a 12 degrees of freedom problem. You have the USV or the manned boat with rotation and translation, that's 6 degrees of freedom. And then you have the recovering platform with another 6 degrees of freedom. And how exactly do you get from 12 degrees of freedom to 0 so you can actually recover safely? And this is what we've done in SealerTech. A little bit about requirements. Performance, we believe that if you look at standards today, launch and recovery is set up to 4 knots, sea state 4, I'm sorry. We believe that with automating the process, you can make it safe, reliable, to be operational to sea state 6. And we've proven that. Speed should be around 5 to 15 knots, depending on the sea state. Recovery time should be very, very fast. You don't want to be hanging between sea and a sky for too long. And of course, we want to have minimal impact on the boat or the vessel performance. On the operational requirements, when you recover a boat in rough sea conditions, you got to have a certain trim angle. And there's a sweet spot of a trim angle that is optimal for every type of boat, but a boat changes its LCG according to where the crew is sitting, how many fuel has landed with finishing the mission, what's the payload today. So you have to have a recovery system that can compensate the longitudinal center of gravity of lifting. Of course, we need to keep the safe crew and the gear. And we also believe that, especially for the next few years, you have to be able to recover dead vehicles. I mean, you have a USV, now it's dead, it's not moving. How do you recover it? On the technical requirements, the range of vessels, anywhere from 3 to 15, even bigger vessels, is part of the requirements. And this is something very important. The solution for autonomous launch and recovery should be the kind that fits any boat, any ship or rig, and any crane or davit. We don't believe in solutions that require the customers to change their boats, to change their davits, or to build stern ramps where they don't need it. Let's talk about the human factor. So we need to get the men out of the loop on the decision making, on timing of actions, connecting lifting lines and painter line. And we want to reduce, and this is very important, we want to reduce the required skills from the operator. We don't want to have operators so experienced that they can be certified for recovering a boat only after 5 years driving one, okay? So we need to design a system that helps the operator be less skillful but still successful in the operation. So I'll start with showing you a short video. We at SealerTech have actually conducted successful sea trials in Sea State 4, in motion, fully autonomous recovery with an unmanned surface vehicles. To what I know today, this is probably the only system in the world that actually have been proven in Sea State 4, and it was also tested in flume test for Sea State 6 with the same results. Okay, unfortunately, we missed winter in Israel, and the highest waves we got was 1.5 significant and 2.5 meters. Yeah, I'm not talking in feet. 1.5 meters significant and 2.5 peak waves. But flume test we did Sea State 6, it works just the same. And just let's go back. Okay, in one word, this video is a little bit censored because we have a few IP things that we cannot really share, but you'll see how we actually performed fully autonomous recovery in Sea State 6. We're very excited. It's a big day. So we developed autonomous launch and recovery based on a cradle that has robotic features, incorporated sensors, which I'll talk about in a few minutes. And it actually recovers an unmanned surface vehicle, Sea State 4, in motion, easy. And when I say easy, I mean easy. I was surprised as a designer with the results because you expect to have failures and that's how it works, but it worked amazing, and this is why we're here. We're here to show that autonomous launch and recovery is already here, and it can be incorporated with the US Coast Guard, with the US Navy, and start having safe operations in heavier sea states. So how exactly do we tackle the challenges? How do we tackle the requirements? First of all, first thing, and that's the biggest challenge, you need to identify with your recovering system the boat that is approaching you and have a capturing system that actually works in every sea state. And that we have achieved by using smart sensors, but also with smart mechanics and robotic capture arms. We can capture a boat where the bow is actually flying all over. We can capture it and pull it inside in sea state 6, and that's a big achievement. There is a certain order to close the 12 degrees of freedom if you want to have safe launch and recovery. And there is a concept that we call the clear sky. I'm not sure if you've noticed, but our cradle doesn't have a structure above it. If you saw other cradle solutions, there always is a structure above that the cradle has to drive into. You have to drive into actually a big, big cage. In my experience, not a very successful one, and also very dangerous. So how exactly does it work? The boat operator, all he has to do is to drive to this green zone, which we call the virtual capture zone, and maintain position. Generally, the identification and capture is done autonomously by our system, and then the boat is neutralized. Meaning, all the boat driver has to do, and everyone here in this room who drove a boat this size know it's not a big task, is to drive to the stern of the cradle. You don't have to ram it, you don't have to have relative speed, and you have to keep somewhere in the area, which is 1.5 wider than the boat, so that was a requirement, and almost 2-3 meters long, so every mediocre driver would be able to achieve, okay? Once he put his boat in this area, and I'll show it again, our sensors using machine vision and RF triangulation, knowing exactly the XYZ and rotation of XYZ of the boat relative to the cradle, operate the robotic capture arms, and from this moment, the boat operator is passive. He's neutralizing the boat, he sits in a chair, and that's it. He finished his role in the launch and recovery process. The same would be applied for stern recoveries. I know that stern recoveries are extremely dangerous. You have to have a relative velocity to drive into a ramp. But exactly at the moment that you reach this turbulent area of the stern, you actually lose your steering capabilities, which causes a lot of collisions and accidents. Let's see that again. Okay, relative velocity is the main cause of accidents in stern recoveries. So we apply the same method. We will install our robotic capture arms with our sensor package on the stern of a ship. And the boat operator, all he has to do is drive to the stern of the ship, maintain general position, and we do the rest, we pull it in. How does the algorithm works? It takes into consideration the sea state versus cruise speed, because the faster you go, the more dangerous it is, and the capture zone is actually different. It's adaptive. The relative position and velocity between the recovering platform to the recovered vessel, all this information is injected real-time on the cradle to a processing unit that makes the decision what is the optimal moment to shoot the capturing mechanism, the robotic capture arms, capture the boat, and that takes the man out of the loop. Now, the capture, as I said before, is the secret recipe. When you have a boat captured by the bow, the process from there and on is much simpler, and the way we designed our system is, since we're capturing the boat outside, and now we're handling it, we can actually tow it not into the cradle, but onto the cradle. So in other solutions using a cradle, if you want to drive by force the cradle on the boat onto the cradle, you have to have the cradle lower, so you don't push it from the stern. So when the cradle is lower and the boat drives in, it actually floats inside. So all 12 degrees of freedom are still maintained loose, and the boat tilts inside and rolls inside, goes heaving up and down with danger of hitting the upper structure. But if you are able to capture outside, you can actually design the cradle to be higher than the boat. So we capture, and then when we pull it on top. So when we pull on top, you have the 12 degrees of freedom starting to lock from the entrance because they're mated from the hydrodynamic forces and the hydrostatic forces. And that's a big, big difference. When you can capture outside, you can design positive flotation cradles and not negative flotation cradles, which in our perspective are dangerous to drive into. I'm going back to one of the requirements that I talked about, being capable to implement this system to any ship or any other platform. So when we designed the system, we decided that any existing David or ship will be able to buy a kit, okay, and use it for installation. So for example, if you would like to install the capturing hook on your boat to be recovered, it takes about 4 hours to install. It weighs about 5 kgs on the bow and another 5 kgs of hydraulic unit inside the boat anywhere you want, very flexible, very easy installation, and with practically zero impact on the performance of the recovered vessel. For the recovering ship, we will supply a control dashboard that controls all the elements of the system, and of course the recovering cradle, which is something you connect to the end of your crane. Simple as that, an add-on system. It will be exactly the same for stern ramps. So if tomorrow the US Coast Guard would like to test a SealerTech launch and recovery system, we will be supplying the sensor package, the capturing system. The capturing system will be installed on the stern of the stern ramp, and that's it. So basically, it's fairly simple installation, minimal impact on the ship design, zero impact on the performance, but dramatic impact on performance and capability. A little bit about international standard, because that have been talked about this topic today and the day before with Jeep Lara. Well, you can read everything, but I would just like to say that from what we've learned doing our sea trials and design work, that you can there's a real need to defining new set of criteria for autonomous launch and recovery systems. The ability to use algorithms and sensors are reducing dramatically the impact loads, the danger factors, and giving you higher capability. So if normal standards are talking about Sea State 4 operational, we think autonomous launch and recovery should be Sea State 6 operational. So going back to the beginning of the presentation, autonomous launch and recovery would actually fill up this gap and help autonomous systems and USVs be fully adopted with Coast Guard and navies. And for the manned market, we will be replacing the weak link of us, the human, the ones that actually makes the mistakes, with something that is much more reliable, and putting the man out of the danger zone, of course. Last word about the future. The future of autonomous recovery systems is very much like the future of all other systems we see in our daily life. AI will come in and learn, and the systems will learn and improve itself from one recovery to the other, gaining data about impact loads versus sea state, versus weight of the boat. All this information will be gathered, which in, I believe, 3, 4, 5 years from now will make this system so safe that no one in the defense industry, of course, will be doing manned recoveries in the future. Any questions? Hi.
Hi. I do have a question. So it relates to, for the system that's doing the automated towing, are there any restrictions on certain types of weather or atmospheric conditions? Let's say you get a sandstorm.
Yep.
I know here we don't get sandstorms, but over there, I know where you're at, they sometimes do. Is there anything that limits it on how effective, or that could be of concern?
Okay. So the answer is that in the system we have been building, you would have a parameter that the operator on the ship will be able to determine how much risk he's willing to take versus the conditions. So for naval forces and Coast Guard, it's really important because you can have a set point that says above this environmental conditions, you don't do recoveries, but then you have to do recovery. So the ship commander set a point that he says, I'm increasing the risk and I'm aware of it, but I'm going to open the window wider from the perspective of what are the limitations, okay? But in this case, everyone knows it and everyone is aware of it.
Also, another question is, on a propulsion system that you might install...
On a what?
On the propulsion system that you install for the boat, is there any restrictions on what type?
No, no restriction
Okay.
whatsoever. Moreover, we designed our last generation to also be able to recover boats that have deployed sonars, like a moon pool with a dipping sonar. And the reason is that we had a customer with a requirement. He said, what if I have a malfunction in the system and it's not being retracted? How are we going to hoist it back? So it's, I don't know if you saw it in the video, it's actually an open hull cradle. It's open all the way in the middle. So we can recover these vehicles as well. Thank you for your questions. Anyone else? Thank you very much.
Okay, everybody, we're going to be taking a little break for lunch, and also we've put together the Promoting Electric Propulsion Competition race videos from yesterday. It was very exciting for the people that were able to be down by the water to see the University of Kentucky pull out an amazing victory. So as you enjoy lunch, go ahead and grab your lunch, come back, and we'll be rolling the videos here shortly. We also will have next technical paper panel that's going to be starting the Naval Unmanned Surface Vessel Requirements and Autonomy Development Panel at 1:30. The moderator is Captain Pete Small, the program manager for Unmanned Maritime Systems. He's already here. He was down by the water a little while ago, so his panel is here. So enjoy the videos, and we'll see you back here at 1:30 for the next panel. Have a good day.